Welcome back, ladies and gentlemen. Next up, we're going to hear how network engineers can be empowered with unprecedented visibility into their networks. It's my great pleasure to welcome the Senior Vice President of Innovation and Advanced Research for Rakuten Mobile, David Soldani, who will be soon followed by Rahul, Atri, the President of the OSS Business Unit at Rakuten Symphony. But for now, ladies and gents, please put your hands together for David Soldani. Thank you very much.
Thank you so much. Not so many people. Hopefully, more people will join the talk. So, welcome to the session. I'm covering my vision towards 6G. Then I will introduce eBPF, this fundamental enabling technology. And then I will show you some applications on the Kubernetes platform. And that is followed by our Sauron eBPF, our platform, where we also have a few demos here in our booth. And then the conclusions. And during the last part, Rahul will join this conversation to present the Symphony's offering. So where are we today? I try to simplify the Rakuten mobile network. So today, we already have in front of us a fully virtualized network, completely disaggregated. And for example, at Rakuten Mobile in Japan, through this innovative architecture and deployment, we managed to achieve massive cost reductions. That is 40% in terms of CapEx and 30% in terms of OpEx. So what you see here already, what you see here on the slide, it is reality. This is what we have, particularly in Japan with Rakuten Mobile, and now this approach is followed globally. I try to simplify where we stand at the moment with the 5G. A rather simple architecture, but what we can see is that we are having today 5G in terms of network functions, and those network functions needs to be run on a cloud infrastructure. And the fundamental enabler to achieve this goal is Kubernetes, like Parta earlier presented our solution, Robin.io. The first step to achieve automation has been with the launch and execution of the Nephew project. So what Nephew, currently ongoing, they already have a release of the project. What it does, it introduces automation so that we have a simplified way to onboard these workloads on Kubernetes. So the fundamental shift here is to move from the traditional virtual machines to container orchestration. So what Nephew allows us is to introduce automation from here down to the cloud in terms of infra resources. They provide also templates for workload resources automation, and also they provide templates for configuration of the workloads automations. So my vision of 6G still at this level, I'm not going into the details. You may see here the difference. And there are two fundamental paradigm shifts. So the first thing, we aim at dealing with cloud-native functions. No more network functions. Those cloud-native functions has to be specified across the whole complete network, radio and the core network. And then we need to reduce the level of complexities in terms of automation. And all this architecture, there's also, my view, will be powered by eBPF. So the question is, what is eBPF and where would that reside? So eBPF, this fundamental enabling technology of the Linux kernel, now coming also on Microsoft's Windows, is available all over the places where you're using the Linux kernel. So that will allow us to introduce programmability in real time everywhere. This is a design of a potential 6G architecture. You see this fundamental enabling technologies on across all network elements, but we also have ability to have on AJP and satellites. We also have a massive adoption of eBPF in terms of the business processes. This is an high-level description of DevSecOps. And BPF plays a key role on runtime security. So if you want to achieve runtime security, you will go for an eBPF-based solution. So now we'll introduce what eBPF is. So after this, I think all of us, we have a fundamental and clear understanding of this virtual machine. So eBPF stands for Extended Berkeley Packet Filter. The abbreviation comes from the origin of BPF, Berkeley Packet Filter, which is in existence already since 2014. But the abbreviation itself, the explanation of this abbreviation, it really does not cover what this virtual machine is all about. So this virtual machine, it is a machine of the Linux kernel that allows us to achieve programmability of the kernel, instrument the kernel in real time. So we don't need to recompile the Linux kernel. It will run immediately after we attach the program in the kernel, and it is portable. You can change various programs in the kernel. It doesn't harm the kernel. You don't need to reboot your nodes, and it is safe. So currently we have 4 use cases, and here I can show you later, if you have time, also what we have achieved at the Rakuten Mobile. 4 fundamental use cases. We introduced security, runtime security, observability. We can see pretty much everything and anything in your cluster, on your nodes. And then it enables us to do a sort of SDN within the clusters and between clusters using eBPF. And then it enables us to trace the performance of your machine and also data profiling. There are a number of frameworks to allow you to use this virtual machine. I'll explain you how that works. So that's the eBPF project. It looks complicated, but it is extremely simple. So think now, I want to program my machine and modify the Linux kernel. What I do is I am writing an eBPF program in C, point number 1 there. I then need to compile it, and the compiler allows me to achieve a bytecode. That is the basic language the kernel understands. Then through system call, those are BPF system call helpers, I'm loading that into the kernel. And then once it's loaded to the kernel itself has a eBPF verifier. It checks that the program doesn't harm the Linux kernel. It's then compiled in real time where I have the native instructions, and then it is attached to specific hooks of the Linux kernel. I have to create also for the communication between the kernel space and the user space where my application runs eBPF maps. So there are types of maps, memory, which I can use to exchange information between what runs in the Linux kernel and the application and vice versa, and also making communications, various programs I'm running across the Linux kernel. So all visibility between the kernel space and the application space or user space is through eBPF maps. It is because of the introduction of the eBPF maps that we say now we have an extended or enhanced version of the BPF. There are various hooks, or we call them BPF program types, I can use to attach my program to specific components of the Linux kernel. So that's the Linux kernel, that's the user space. I can attach my programs to system calls for security, for example. That's one of the use cases. To sockets, I can tap any sort of virtual interface in the kernel. I can attach to the network interface cards. So then I'm offloading the kernel itself. And also I have ability to attach to the process themselves using uprobes. Okay, I made a demo but I think nobody's won already. So this is just a demo to show you what a eBPF program is and how we bring that into the kernel, and then what you get on screen. So what this small program does, which is listed in here, so it's just a piece of C code. It will allow me to capture the packets that achieve at my local interface and say hello world. Okay, so it's just an example. So that's the program itself. You will see here in terms of C++ instruction. This is an helper that allows me to print hello anytime the event reaches my network interface card through that XDP, which is an eBPF hook or eBPF program type. I'm using that section, which is just a macro that allow me to attach the event and then trigger the event itself. Then I need a make file so that I can compile this program. And once that is compiled, I need to load the program into the Linux kernel, and here I can use the BPF tool, which is provided by the VM machine, eBPF itself. So using the BPF tool, I attach the program, I load the program in the Linux kernel, and then I can see where the program resides with another BPF tool command, and then I attach the program to that particular BPF program type, the XDP. And I can see that it's really attached. So it's the program 131. Then how can I test it? Easy. What I do, I send a ping to my local host. This is exactly the interface where I attach my program. And once you ping here, then you can trace the BPF program and you will find that hello is printed because packets are reaching your interfaces. And in this case, it's been 559 times because I have also introduced a counter that anytime this event is called, it is incremented. So that's all. So this is what eBPF is, and an example skeleton and framework for you to program the Linux kernel in real time without compiling the source code. So why was so important this enabling technology? Because it introduces programmability on Linux kernel without awaiting anything. I can do that in real time. And in real time, I can modify the function of the kernel. It is safe, it is portable, it is scalable, stable, and it introduces visibility, control, and performance. So by those programs, I can observe anything and everything that happened in the kernel space, but also in the user space, as all the containers ran on a single kernel host. And then it has a very little overhead, so I can program the Linux kernel, and then it doesn't harm the kernel. It also is not noticeable in terms of performance. Okay, now it is particularly valuable for Kubernetes. I can show you here an example of improved performance. This is taken from our friends from Isovalent, Cilium. So my friend Thomas Graf and Litz Rice, they represent well the enhancement we are having across the stack. This is a network node, so this is and that the corresponding networking stack. When you run a container in your cluster, you would simply duplicate the networking stack. You can see here that you have the network namespace around your container as you are having in the Linux kernel. So you introduce 2 times the overhead. Use eBPF, you can get rid of this infrastructure below. So you have a direct path from your network interface card to the applications and vice versa. And the performance are improving on a factor 2.5 to 4.3 depending on the IP tables you're having in use in your Linux kernel. It reduces, if you think of a service mesh, any instrumentation you want to do on your application, you need to use sidecars. So sidecars means an additional piece of software addition within the container that runs your application. You see here that the network stack is rather convoluted because you need to make use of the loopback interface to provide a packet and then processed by an envoy proxy in this case. With eBPF, we can get rid of n proxies and reduce everything to one single proxy if it is really needed. And on eBPF, I can also run security. Like here, you might use Istio in your cluster. You don't need to use Istio. It's a huge, powerful tool, but it's really cumbersome. So we can use eBPF and bring the PKI at eBPF level, introducing MPLS and having only a single CA. About security, also typical application, if you think of runtime security, the execution engine runs in the user space. So that means if you have an intruder, like here, a pod evasion, that is harmful to the kernel, you may detect in the kernel, then you notify again the application, and the time that is executed by the application is such that the malicious activity can continue. Using eBPF, like I'll show you later, we can run the inference directly into the Linux kernel and kill immediately the malicious pod. So what we have done at Rakuten Mobile, and then Rahul will introduce you the continuity at Symphony offering, we have developed our own platform. We call it Southern, and Southern supports 4 use cases. Here you see the high-level architecture. You always have ability, those are our eBPF programs that they run into the Linux kernel, which are loaded using our agent. So you do have one agent for each node. It is a daemon set, and then you need to have a controller and operator that configure the agent. And we have already ability to attach our program all over the places. This is an example architecture of Southern for observability. Here you have our agent, operator, and then services exchanged through the API server, so our operator can be aware of everything and new pods, and then we can decide through our agent where to attach our programs depending on the use case where I intend to extract information. That's why we achieve profound observability. All what happens here is in real time. Now, looking at the deployment on Rakuten Mobile Network, and here behind here we have the screens with some use cases and demos. We have achieved to bring eBPF on our devices and measure end-to-end and hop-by-hop latency, jitter, point of service in real time. So if you want to measure your transport network layer, please come and see us. We can show you how we have achieved that at the Rakuten Mobile. We also have profound observability, as I showed you earlier, and then runtime security. We validate our proof of concept through a number of use cases, and we demonstrated at Rakuten Mobile that we have ability to detect incidents on real time. I don't know what's publicly disclosed. The network was down 2.5 hours. With eBPF, we had ability to detect the file size exceeding the router capacity. Measurement all over the places, generating synthetic packets. And then we have ability to measure energy of any application, workload, and then pods and corresponding interfaces. We have achieved also ability to capture the traffic between the RAN and the core and measure end-to-end latency. So think of in the kernel, I can measure the latency. It takes the time, takes a mobile to establish a session. Then ability to tap all over the places. And the last one is about security, runtime security. We have made available a lot of documents, and today we have launched our white paper. You may download our white paper. It's 25 pages. And then associated with that, we also disclose on a 30 pages document more details for the people that are interested to work on eBPF. So Rahul, now we want to understand from you more about this technology and particularly how Symphony will make use of it.
Thank you, David.
in short, a lot of information. Thank you. I think the network of the futures are dynamic. You have intent flowing in from different use cases and configurations and use cases. And if the networks are dynamic, your observability cannot be static. You cannot be monitoring the network 15 minutes out or half an hour out and still say that your network is performing well. And that's where the eBPF comes into picture. You can have more real-time dynamics into understanding your network is, what your infrastructure is, what your applications are, and then how the services are. On top of it, what eBPF does is you can configure it. It goes to the kernel level, it goes to the infrastructure level, you can monitor it, you can figure out the security challenges, and also trace the packets. Earlier, the situation was that it's difficult to load the software stack into kernel. The kernel is the heart of the platforms where you don't want to touch them. But with eBPF coming in, you can load them as libraries, you can configure them runtime, you can reduce the noise, you can increase the noise, you can figure out what telemetry makes sense to you and write the policies and use cases on top of it. And that's where I think eBPF is special. And that's how we are using it in our observability platform, right from the heart of the devices on the customer hand, to the radio equipments, to the transport equipments, and to the core network. You can actually monitor a lot more. The transparency is a lot more, and the real-time observability is a lot more. And how you use that information for real-time orchestration, real-time intent-driven actions is up to you. We can surely talk about it, what the use cases we are running in Rakuten Network today. Thank you.
Do we have time for questions?
We do have time for questions. Are there any questions from the audience for David or Rahul? Ladies and gentlemen, we have one question. No. Ladies and gentlemen, big round of applause once again for David Soldani and Rahul Atri. Thank you.
Thank you.
Thank you.